In our previous example, we solved a system of three homogeneous equations, differential equations, and when we computed the eigenvalues of the coefficient matrix, they were three distinct eigenvalues, and we had a theorem that said how we could solve it. Remember, the first term was something like C1, an arbitrary constant, times capital K1, which was an eigenvector, times e to the lambda 1t. Lambda 1 and K1 were an eigenvalue-eigenvector pair. Well, in this example, we're going to figure out how to solve it when they are not distinct. It's not quite as easy. It's not so bad. It's not bad at all. The problem comes in that if you have two, this is just an example here. Suppose we had lambda 1 and 2 both being -1 and lambda 3 being 8, which means that the characteristic polynomial would be for, in this case, it would simply be factored, would be lambda plus 1, lambda plus 1, lambda minus 8. In this case, we're still going to find three linearly independent eigenvectors. Of course, we'll get one for lambda equal 8, the unique lambda. In this one, where they're not unique, we're still going to find two eigenvectors that are linearly independent, that are going to make the solution look just like, very similar to the previous problem that we did, previous example. So let's dive in. Here's our example. X prime, y prime, and z prime are equal to a function of x, y, and z, a function of x, y, and z, and a different function of x, y, and z. And the first thing we want to do is locate the coefficient matrix, which would be 3, 2, 4, 2, 0, 2, 4, 2, 3, and find the eigenvalues associated with that. And how do you do it? Well, you take the determinant of a minus lambda I. And remember what a minus lambda I looks like? It looks just like the matrix A, only along the diagonal you put a minus lambda, minus lambda, minus lambda. So the rest of it is just like the matrix A. This one is just negative lambda because it would be 0 minus lambda, so negative lambda. And the vertical bars are what is the determinant. So we're going to find this, and then we're going to set it equal to 0 and find the characteristic polynomial. So to start off, I would get 3 minus lambda, I'm going to go across the top row, times its cofactor, which is the determinant of this matrix. Negative lambda, 2, 2, 3 minus lambda. And then remember, I have to alternate signs. This one, exactly the way it is. This one, you have to negate it. If it were negative, you'd make it positive. If this is positive, so we'll make it minus 2. Times the determinant, times its cofactor, which is the determinant of, cross out that row in this column, 2, 2, 4, 3 minus lambda. And I need one more. I will go right here. I will say plus 4. And I get rid of its row and column, and I get 2 negative lambda 4, 2. And without writing out and going through all of the details, just as a reminder, this determinant here, any 2 by 2, you take negative lambda times 3 minus lambda minus 2 times 2 or 4. So after you write all that out, and then minus 2 times this product minus that product, plus 4 times this product minus that product, and you do a bunch of algebra, or maybe I should just say arithmetic, we end up with that equaling negative lambda cubed plus 6 lambda squared plus 15 lambda plus 8. And if I wanted to call this f of lambda, that would be fine. But this is the characteristic polynomial. And So I'll find the zeros or the roots of that polynomial, or I could just set it equal to 0 and say solve it. You get the same results. I'm looking for all three values of lambda. That'll make that work. So just as a reminder, how would we look for a first factor? Well, let's see, the coefficient of this is 1 or -1. This is the constant term is 8, so I want to look at the factors of this divided by the factors of this. Since that's a 1 or -1, all I need to look at is plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And if I plug in a 1, would it give me a 0? I would have a -1 plus 6 plus 15 plus 8, no. But if I plug in a -1, it's going to work. A -1 is going to give me an 8, a -15, a positive 6, and a positive 1. That's 0. So f of -1 equals 0, which implies, I'm going to go ahead and write this down, x lambda plus 1 is 1 factor. So if we did synthetic division, putting a -1 in the cup and the coefficients being -1, 6, 15, 8, we'd end up finding out that it's x plus 1 times some quadratic. And I'm going to save the arithmetic, and I'm just going to show that f of lambda is, of course, lambda plus, actually it had a negative sign in front of it, but that doesn't affect the zeros. Lambda plus 1, lambda plus 1, lambda minus 8. This is the factored form of the characteristic polynomial, which tells us exactly what the lambdas are. Set all three of them equal to 0, and I get lambda 1 equals -1, lambda 2 equals -1, lambda 3 equals 8. So it turns out this example I took was from this example we just looked at. So we have three non-distinct eigenvalues. That's the problem. It's not a big problem, but we're going to show that we can get two linearly independent eigenvectors, capital K1 and capital K2, associated with -1. And then we'll just get this one, capital K3, the usual way. All right, let's do the multiple case first. Let's start off with lambda equal -1, and I want to find K1. So lambda being -1 means this equation is how we find K1. A is our coefficient matrix. And why do I have a plus I here? Because it's supposed to be A minus lambda I. But lambda is -1. So minus lambda is actually a positive 1. So it's just A plus I times this eigenvector must equal the 0 vector. So I'll come to this in a minute where I said note that A is symmetric. We'll come back to that later. A is called a symmetric matrix. If you remember that from a linear algebra class you've had, we'll talk about that in a minute. So this equation, hopefully you can tell me what A plus I is. Just take A and add the identity matrix into it. The only elements that change are the diagonal when you add I, because it's 1 on the diagonal. So we're just going to add 1 to the diagonal elements. So instead of 303 on the diagonal, it's 414. So that's A plus I right here. A plus I times K1 equals 0. Let's solve this. We're just going to use Gaussian elimination like we always do. 4, 2, 4, 0, 2, 1, 2, 0, 4, 2, 4, 0. Well, this is not going to take much work, is it? Those rows are all multiples of each other. That means two of them can just disappear, turn them into zeros. for example, just this row, you do row 1 minus row 3 minus row 1. Gone. I'm going to rearrange the rows, which is a valid row operation. I'm going to put the 2, 1, 2 on top. But that 2, 1, 2, if you multiply it by -2, you get -4, -2, -4, and you could add it into that row and it would turn into all zeros. So do some row operations. We did it in our head. We get 2, 1, 2, 0, and then zeros. All right, well, the only equation we have is the top row. And we're looking for capital K1, so maybe I'll call this the little k1 row, the little k2 row, the little k3 row. So K1 is just the vector K1, K2, K3, lowercase letters. That equation would be 2K1 plus 1K2 plus 2K3, and that's equal to 0. So we have an infinite number of possibilities here. So let's just narrow them down. And you wouldn't have to do it this way, but I'm going to set K1, choose. K1 equals 0. Okay? So what does that mean? K2 would be equal to -2 K3. Now, we've got an infinite number of possibilities here. Choose, I'm just going to say K3 equaling 1. That way I won't get any fractions. If K3 equals 1, that implies K2 is equal to -2. This is one eigenvector. I'll call it K1. Capital K1. Well, yeah, that's what I called it up here. K1 equals, let's see, K1 is a 0, K2 is -2, K3 is 1. All right, well, this time we're going to do it again, but we're going to choose something different. I'm not going to choose K1 equal to 0. Maybe I choose K3 equal to 0 this time. And if K3 is a 0, what does that mean? These two add to 0. So K2 would be equal to -2K1. So let's make K1 a 2. Choose K1 equal to 1. And that would mean if K1 is a 1, this is -2, K2 is -2. So you choose, for starters, I chose K1 to be 0. The next time I did not choose K1 to be 0, I chose K3 to be 0. This ensures that you're not going to end up with multiples of each other for these vectors. Notice that capital K2 is that. They are not multiples of each other. You couldn't multiply something by one of them to get the other. Therefore, they're linearly independent. So I called it K1 and K2. So I really had a lambda 1 and lambda 2 that were both -1. This is the K1 and K2 that will go along with them. So that's the only difference between this and the previous problem that we had. I'm going to run out of room, so I'm going to say here, for lambda equal 8, what do we have? We have, and just to delineate, should have started in blue, I'm going to use a different color. For lambda equals 8, we get A minus lambda 8I, K3 equal to 0 vector. And we repeat what we just did. So let's see if we could just let's just set this up. What would a minus 8i be? A is up here. I have to subtract 8 from the diagonal. 303 became negative, I have to subtract 8 from the diagonal. So it's going to be -5, -8, -5 on the diagonal. The rest of it stays the same. 2, 4, 4, 2, 2, 2. K3 is equal to the 0 vector. And we proceed as, I'm going to say, linear algebra, or I should have said Gaussian elimination, gets us down to a matrix that looks like 1, 0, -1, 0, 1, -1/2, 0, and then all zeros. So from that, you end up getting some eigenvector, and it turns out that the one I chose, I started off by saying choose K3 to be the number 2. After I worked out some stuff like this, I ended up with K3 equaling 212. You might have done it differently, and you might have come up with K3 being 424, or -2, -1, -2, some multiple of that. So finally, our equation, our solution, capital X, is equal to C1, K1, which is 0, -2, 1, e to the lambda 1t, the lambda eigenvalue with these two is -1, so you just get a -t, and then plus C2, K2, e to the -t, and the last one we'll use K3, so it's going to be C3, K3, e, and that was an 8 for the eigenvalue. And this gives us the solution where we had repeated eigenvalues. It looks very similar to the previous one where we had distinct eigenvalues, but that is only because we were able to find two linearly independent eigenvectors, K1 and K2, both of them associated with lambda being -1. That doesn't always happen. So I'm going to close this video out by telling you a time that it will always happen. When your coefficient matrix is a symmetric matrix, you're going to have repeated eigenvalues that are not a problem. You will get 3 linearly independent eigenvectors. And in this case, 2 of them were associated with the same eigenvalue.